Hello, my name is Sangeet Sagar, and today I will present the poster RescueSpeech, a German corpus for speech recognition in search and rescue domain. This work focuses on speech recognition for specific related field, that is, search and rescue domain. This is a very critical area, actually, where quick and accurate information is very essential for saving lives, as it involves, saving or locating and rescuing people and providing medical assistance to them who are in distress or danger or who are trapped in inaccessible locations. However, this involves a complicated situation that is very stressful and heightened emotion, and thus the speech of a person that is being rescued or who is rescuing is affected. Where this work would release an annotated speech data and propose a system with a benchmark that aims to tackle these challenges. Now let's see what is this RescueSpeech dataset. So RescueSpeech is a German speech dataset that aims to tackle the challenges of lack of speech data and robustness to the search and rescue noise, that is SAR noise in the ASR. It includes recordings from native speakers of the language speaking in a kind of radio style conversation, radio style dialogue. Although this is like a very small data set, 2 hours of data set, it has a wide range of applications, for example, robot control or using it to build speech recognition systems to support decision making for such a hostile situation. Now we release the data set into two sets. That is, we call it the RescueSpeech clean set and the RescueSpeech noisy set. The RescueSpeech clean set is simply the segmented recording with an average length of around, I guess, 3 seconds. However, the noisy set is prepared by artificially adding noise, keeping in view of the low noise profile of the clean surroundings of the clean recordings, actually. And this is done to mimic the conditions from search and rescue event, because an audio captured from a search and rescue event often contains certain kinds of noises like chopper or let's say engine noise or static radio noises, etc. However, we also believe that this has a limitation, like artificially noise injection has a disadvantage, that a nonlinear relationship between a noise and a speech that is present in a naturally occurring noisy surrounding or noisy utterance is absent in artificially synthesized recordings. So here I show the statistics, the distribution of the data set. So in the clean set, we have around 2 hours of data set combining train, valid, and test, and using the clean utterances, we synthesize noisy utterances by artificially adding noises such as emergency noise, breathing noise, engine noise, a chopper noise, and a static radio noise. And we use these noises from the audio data set, and overall we come to around 12 hours of audio recordings that is noisy. To propose a benchmark on our dataset, we have used following models for ASR training: CRE-NN, Wave2Vec, Wave-LM, and the state-of-the-art Whisper. So CRE-NN is a traditional model that is used in ASR, and it's a combination of CNN, recurrent neural networks, and dense neural network. We have also made use of pre-trained models such as Wave2Vec and Wave-LM. These models rely on self-supervised learning scheme. On the other hand, we have Whisper that we have used for speech recognition again, and it was kind of a state-of-the-art model for ASR back when we were writing this paper. To denoise our noisy speech, we use Ceph-Former here. This is the heart of the Ceph-Former architecture. So it is a multi-head attention transformer-based network initially proposed for speech separation, actually. And here, our idea is that we would like to separate noise from the clean speech. It uses a fully learnable masking-based architecture composed of an encoder, a masking network, and a decoder. The intra and the inter transformer that you see here, the intra transformer models the short-term dependencies, and the permute block rearranges the output dimension. And further, the inter transformer block models the long-term dependencies. Now let's explore what fine-tuning strategies or how our experiments were set up. So we have defined four strategies for fine-tuning our noise robust ASR system. The first is clean training. So in the clean training, we use the pre-trained model. First, fine-tune on a large data set such as Common Voice and Microsoft Deep Noise Suppression Challenge data set. So this is called as clean training because we train these ASR models and speech enhancement models that we discuss here on a large data set, and then further fine-tune on RescueSpeech clean training dataset for domain adaptation. The next is multi-condition training. In the multi-condition training, we use equal proportion of clean and noisy recordings and from the RescueSpeech dataset and fine-tune our ASR model. In the third strategy, that is model combination 1, that is independent training, we basically combine the speech enhancement model and the ASR model. So the speech enhancement model that you see here is kind of a frozen. It's pre-trained and fine-tuned on a RescueSpeech dataset, and it's combined with the ASR model here. So first we have the pre-trained enhancements model that is firmer, and it is further fine-tuned on RescueSpeech noisy dataset, and the enhanced. So once it's trained, we use this model to clean the noisy recordings, and the enhanced recordings are further fed into the ASR model to perform speech recognition, and word error rate and other metrics are recorded. In the last strategy, that is the model combination 2 joint training, we combine the enhancement model and the ASR model. So basically, when we combine them, we unfreeze them. This means that the gradients that is backpropagated by the ASR is fed directly into the ASR in the enhancement model. So we believe that this has the advantage that the ASR model dictates the enhancement model on how it should be cleaning the speech that results in a best possible word error rate. Let's see some results here. So we have categorized into 3 parts: the pre-training, the clean training, and the multi-condition training. So in the pre-training stage, we do not fine-tune on any RescueSpeech dataset, but we only use publicly available large datasets such as Common Voice. So here we see the but for the test we use the clean RescueSpeech dataset and the noisy RescueSpeech dataset. So here we observe that Whisper has recorded a best word rate on clean speech, while on noisy audio, all the models perform equally bad. In the clean training, again, we fine-tune for the first time on the clean training, we fine-tune on RescueSpeech only clean dataset, but we test on both clean and noisy dataset also. So we again observe a further improvement on word rate with Whisper. From 27, it went down to 23. But on noisy, the performance is more or less relatively equally bad still. Now, when we do multi-condition training, that is equally mixing clean and noisy recordings, we observe a better word error rate, even better word error rate with noisy test inputs. However, with the clean inputs, it has there has been a little degradation on the word error rate. Here we see the log power spectrogram of clean, noisy, and subformer enhanced utterances. So here we have the clean recording, and here we have the noisy recording, and the type of noise is emergency vehicle siren noise. And here we have the enhanced utterance that is cleaned by the subformer. So by visual inspection, we can see that these bright patches, that is the noise itself, have been eliminated with the enhancement model. Here I show how, so when we combine the model, and that is the model combination 1 and the model combination 2, that is the independent training and the joint training here, we show the speech enhancement metrics like SISNR, SDRI, PSQ scores, and STOI scores. So looking at these, we see that when a joint training is performed, we have better speech enhancement metrics. For example, compared to 6.5, we have 7.4 with Whisper, 7.4 we have 8, and same with other metrics. So this means that upon performing joint model training, we have a better enhancement, because the gradients from the ASR is actually helping clean the speech in a better way. And in terms of word error rate, we show how the word error rate varies with independent model training and joint model training. So we observe that with Whisper, we have the best performance is 45.29 compared to 48.04 with joint model training. So we believe that with 48.04 with independent model training. So we believe that this joint model training definitely helped achieve a better word error rate. Now let's talk about the conclusion. So in this work, we saw about how we address challenges related to search and rescue domain, particularly when doing speech enhancement and speech recognition, that is noise robust speech recognition. Via this paper, we released the RescueSpeech dataset, that is first ever publicly released audio dataset captured in a search and rescue mission. And despite leveraging very advanced model that has been pre-trained on tons of data, we still achieve a word rate of 45.29, which is not very promising for such a critical situation. Now let's see some audio utterances that were cleaned by subformer model, and how is the transcript varying. So first I'll show you, I'll just be showing for one noise type, that is emergency vehicle and siren noise. Let's hear the clean audio first.
Wenn der Auftrag nicht durchführbar ist, abbrechen. Wir haben jetzt einen Trupp auf dem Weg zur verunfallten Person.
And let's observe the noisy utterance that was artificially synthesized.
Wenn der Auftrag nicht durchführbar ist, abbrechen. Wir haben jetzt einen Trupp auf dem Weg zur verunfallten Person.
And let's see the enhanced audio that was cleaned by the subformer enhancement module.
Wenn der Auftrag nicht durchführbar ist, abbrechen. Wir haben jetzt einen Trupp auf dem Weg zur verunfallten Person.
You can also look at the transcript here. There's a very little degradation in the word rate. And here we show the log power spectrogram here. These extremely bright patches here, these are the noise that have been seen to have been eliminated by the subformer enhancement module. We have publicly released the source code and the model itself, which can be downloaded from Hugging Face. It's available here so this is the QR code for the dataset, and this is the QR code for the GitHub repository, and we have made use of SpeechBrain throughout our experiments to train our models and evaluate our models. So one can go here and check out our repositories and even download our models from Hugging Face. Thank you very much.